Okay, you guys, so we are going to take some notes on crystal defects and how they occur. Now, what I don't have it posted yet, so I can't completely show you, but you are going to see by the time we're doing this under Unit 1 reference materials. I'll put it here, but I'll also put it in today's post. You're going to need to either print up if you can. I'm not going to have copies in the atrium for you because I'm still in Texas, but print up if you can this BP4 packet. It's our last notebook packet of this. And this unit is a long unit. It's longer than normal because of COVID, but it does tend to be a longer unit. But print up that BP4 notebook. If you can't do that, don't let that be an excuse to not do your notes. You can have an electronic copy. If you want to type it in, great, or just have an electronic copy that you end up transferring over to a notebook. But you need to first start by getting that. So I'm going to have it under Unit 1 reference material. I also, once I get, this is something you're going to be doing on Thursday. Once I get that post up, I'll go ahead and stick it under Thursday's post as well. So once you have that, it looks like this. So this is what you should be printing up, or you're just making an electronic copy of. And what we're going to do is we're going to be filling out this first page of notes. So that set of notes goes with this handout right here, this presentation. So what we're getting into, and crystal defects, when we use the word defect, you think, oh gosh, this is a bad thing. It can't represent anything good, but defect really just means something different about its continual crystal structure. So in the world of material science, what do we call a crystal defect? Well, it's an impurity or a disruption in the pattern of the arrangement. If you look at that notebook, the very first picture, see if you can find the disruption in that crystalline structure. There's an inconsistency there. See if you can find it. And in that inconsistency, it distorts the crystal. And really the big thing it does is that the second red word, it affects its physical properties. So we disrupt the pattern, which affects what we see, the physical properties being disrupted. It's not really a bad thing. It just simply changes the material. So it gets a bad rap with the word defect, but it really just changes the material. So steel is a crystal defect that is made into a much stronger material than just iron. What's the defect? We actually add impurities on purpose. We add carbon into iron to get this steel. So I don't want you to think, oh my gosh, it's a defect. There's something wrong with it. It's not a consumer defect. It's not a product defect. It's just the term we use to talk about when we mess with crystals a little bit. There's three main ones that we're going to talk about when we talk about crystal defects, and that's what your next part of this is going to highlight. So the first is a line defect. When we look at a crystal and we talk about a line defect, this is regions where atoms are not perfectly aligned. So this picture should look a lot like the very first picture in your notes in the Unit 4 packet. I'm going to move myself maybe a little over here. But here's our issue with the line defect. So if we look up here, we have 7 atoms going across, 7 atoms, whoops. As the crystal was being made, it's like all of a sudden Zelinsky tried to make the crystal, and we went down to 6 atoms. It's still can bond, but it changes what's going on with this crystal structure. So what is the impact? Remember, you guys, you can pause at any point. But our impact is a very small amount. It becomes more workable. If we have a large amount of line defects, it becomes less workable. So just a little bit of issues, a small amount of line defects, it becomes more workable. Large amount, less workable. And over time, it creates what's called work hardening. So work hardening is when working a metal, the dislocations, they kind of all get jammed together, they get pinned together, and it makes the metal harder. That can be a good thing. Like, we don't always want metals to be soft. We at some point need metals to get worked and be hard. Whenever you think of forgers, pounding and hitting on metal, there's purposes behind that. We're going to be getting into that. This next unit, we talk even more, but you're going to even see it in the next couple of days when we are talking about words like work hardening, annealing, things like that. Okay, so line defect is the first type. Another type is called grain boundary defects. So this is places in the polycrystals where grains meet. So remember, these are all different grains here, and the lines where they meet, those are called grain boundaries. And we could have defects along those grain boundaries. So grain boundary defects, right here where those grain boundaries meet. So what does that mean? Okay, if we have a bunch of small crystals, so smaller crystals means more boundaries and it means it's less workable. So this would be an example of a bunch of small crystals, okay? And we have a bunch of line boundaries here. It makes the entire metal, and really I'm going to use metals as my example. Most of the time we can manipulate polycrystals with metals easier than anything. So if we have smaller crystals, more boundaries, less workable. If we have larger crystals, we have less boundaries and it becomes more workable. So there's things we can do to manipulate the size of those polycrystals to make them more workable. And this is the big thing. I think I need you to make just a few changes on that handout. If I didn't catch it before, I'll see if I can remember to do that. But the big thing to catch here is heat treating metal. So we hear about this in industry. Heat treating metal can change the crystal size and the crystal type. And we're going to be playing around with that in the next couple of days with the lab with the bobby pins and the aluminum or the paper clip. It's not aluminum, you guys, sorry. So heat treating it can change the amount of polycrystals, the size of the crystal, but it actually can change the type. What do I mean? Go back to the packet before. It can literally change from FCC to BCC, so face-centered cubic to body-centered cubic, or it could change from hexagonal to a different shape. So in heating it, we can change the shape of the metal, and it's kind or the crystal that makes up that metal, and that's quite interesting. There's a third type. I'm going to have to make my little face quite a bit. Oh, there we go. Now I'm really tiny, which is fine. So there's a third type of crystal defect that is called, Zelensky, what did you just do? I really just want to be back here. I just don't want you to have to see all this stuff. Can I get rid of that? There we go. Okay. It's called point defects. And there's three main types of point defects. One is called a vacancy. And this is when, like, look in here, an atom is actually missing. It should be in there, but it's not. So an atom is missing in the crystal structure. The impact of this is it tends to make that metal, that crystal, harder. Interstitial, so we have another type of defect called interstitial, and that's whenever atoms are inserted in between the gaps of the larger crystal atom. So, here is the larger crystal atom, and this honestly could be iron. So when you think of iron and carbon combining to make steel, iron is a huge atom. So these bigger ones would represent the iron atom. These tiny little black atoms here are carbon atoms. Carbons are much smaller. If you've been in a chemistry class, think iron atomic number is 56, I think. I'm going off of memory. So it has 56 protons, where carbon is 6, only has 6 protons. It's much smaller. In interstitial, those little carbon atoms can fit in the gaps of the already existing crystal structure of the iron. So that's a certain type of alloy that can be made. Interstitial point defects create alloys, and the specific alloy it creates is steel is one example. It's not the only one, but it is an example of it. Then there's substitutional. So substitutional is another type of alloy that can be made. It's a type of point defect, creates an alloy like brass or bronze. And this is whenever a new atom replaces some of the original atoms. So in here, whenever we're making brass or we're making bronze, we have two different metals that are going to combine together to make this. I don't want to give too much away because I hope we're going to be doing this when we get into our metals unit. I hope to see some of you. I don't know I hope we don't do this virtual for the rest of the semester. But, when we make brass, we are taking one type of metal and we're actually pulling out some of the atoms of that one type of metal and substituting in a second type of metal in there. Brass is like this. Bronze is another example of this. So that gets us into, this beginning idea. You're going to finish off today with doing an activity that actually goes back to this idea of just being able to look at, and I'll talk it out here in a second. I just took still pictures of this demo apparatus that I have that will let you kind of recognize the grain boundaries and work on some of the language with this. So let me pull out of here and let you see the handout again. If you go down to page, it's always funny to watch where my little face pops up. Kind of scary. But if we go down to, oh, I thought I had these numbered. If I don't, I need to, or maybe I do, and it's not showing up here for some reason. This is where I want you to play around with, and there's more than one correct answer. So you're only going to work with. This is a BB board that I have, and I just took some still pictures of, and I believe it's this page and then the next. Yeah, or I don't know if that all fit on one page. Maybe it. No, it did fit on two different pages. So what I want you to do with this is in each of the pictures, identify, like it says, 2 areas of crystalline structures, 2 grain boundaries, 2 vacancies by circling and labeling. So pretend like this whole thing is a polycrystal. Can you find one of the grains? Can you find another grain? Use a different color highlighter to represent the grain boundary. And then somehow, like we see a vacancy here, I see a vacancy here. Do some other, and you can do this electronically. I don't know how you mark up this stuff, but you guys are better at that than me. But if you print it up, obviously you could just use highlighters or markers to do that. So for rest of class, I want you to work on these 4 pictures that I think are on 2 separate sheets of paper. And it's having you do the same thing throughout. And your answer might not be the same as a friend's answer, and that's okay. And then tomorrow, or the next time we meet, which I don't know if it's tomorrow or not, we're going to be working through this part of the activity. So that's why you have to get the copper wire. You've got to get that baggie of stuff before I see you in class next time, because we're going to be doing this together. Okay? I am going to end it for now, and we will talk to you guys soon. We'll see you later.